Hello everyone. In this lesson we're going to look at light, energy, electrons, and atoms and how all of those are related. Now to get into this a little bit, we first need to understand about light as a part of the electromagnetic spectrum. So you guys probably all remember that light is just the visible part. That's the part we can see, but light is just an electromagnetic wave. That means it's composed of an electric field, that's this blue line here, and a magnetic field. That's represented by this red line here, that vibrate at right angles to each other and then move in a direction perpendicular to both of those. And this shows the whole spectrum of light. Over here you can see you've got this little segment that's visible light. Up above that is ultraviolet, X-rays, and gamma rays. Those are higher energy. Below that is infrared, microwave, radio waves. It's lower energy. So light is actually part of a spectrum of waves. We think of light as a wave a lot, although sometimes it makes more sense to think of it as a particle. And these waves, changing their frequency or their wavelength, changes how much energy they have. Now, why do we think light's a wave and not a stream of particles? Well, actually, we think it's both. For a very long time, light was actually thought of as a stream of particles, and Isaac Newton published a lot on this. He thought it was a stream of particles because light moved in straight lines and cast shadows and could reflect off of a boundary, much like a billiard ball would reflect off of the side of a pool table. But then there was a guy, Young, who did this double slit experiment where he took one stream of light, and that's what these lines represent here, and shined it through a double slit pattern, and because of that he got areas of high and low intensity, or bright and dark, on a screen. And the way we think about that is like if you dropped two pebbles in a pond, they would create circular waves that would move out, and sometimes they would interfere constructively and sometimes they would interfere destructively. When you shine this light through the double slit, it's like you get two new waves that bend through there, and sometimes they interfere constructively and sometimes interfere destructively. That can only be explained by wave behavior. Refraction, the bending of a wave as it changes media, can only be explained by wave behavior. And even breaking white light into colors makes sense under wave behavior of light. That's called dispersion. So the scientific community came to agree, yep, light is a wave. Einstein said, well, it's also particles, and won a Nobel Prize for that. Now, interesting thing about light always moves through a vacuum at the same speed, 300 million meters per second, and that's true of all radiation, electromagnetic radiation, not just visible light. So radio waves and gamma rays and visible light all move at the same speed through a vacuum. But when they move through something that's not a vacuum, like glass or water, they do slow down a little bit, which is why we get refraction. Okay, so like I said, light's a wave, and to understand what that means, we need to know a little bit about waves. Waves have a speed, how fast they move from one place to another, a frequency, which is how quickly they oscillate or vibrate up and down, a period, which is the time for one oscillation, a wavelength, which is the distance between identical points on adjacent waves. Usually we think of wavelength as from crest to crest, and amplitude, which is how far that wave vibrates from equilibrium. So from the top of the wave to the bottom of the wave is actually twice the amplitude. From the middle to the top is one amplitude. Frequency is given the symbol nu. So that looks like a V, except this side is a little bit curvier usually. So you'll also see me write F because I'm a physics teacher. Chemists like to use nu. And it's, the, like I said, number of waves that go by in a second. It's measured in hertz. We'll also see gigahertz or megahertz. Those are just prefixes. Gigas times 10 to the 9th, megas times 10 to the 6th. Period, sometimes we'll use period, which is the inverse of frequency. So instead of waves per second, it's seconds per wave. Wavelength is the distance between identical points on adjacent waves, measured in meters, and speed, v for velocity, is how quickly the wave moves. And this is an interesting equation. You can find the speed of a wave by multiplying wavelength and frequency. So v equals lambda nu is an important equation to have. And then the amplitude, which is the distance between equilibrium and maximum displacement, is related to the intensity of a wave. And for sound, that's how loud it is. For light, that's how bright it is. Both of those are waves. Now, light and energy, it was discovered that the more frequent a light wave is, or an electromagnetic wave is, the more energy it carries. So that's pretty obvious, just heating something up. When you heat an object up, it starts getting red, and then it moves to yellows, orange, yellows, and it'll actually get blue hot, white hot. So as the colors get more blue, this is actually giving off more heat, and so we're able to relate energy and frequency with Planck's constant, and that's this h here, which is 6.626 times 10 to the negative 34th joule seconds. Remember, joule is a measure of energy. When we take joule seconds times per seconds, we do end in joules, and this down here, since the speed of light is constant, we can replace frequency with c over lambda, which is wavelength, and so we can also say that E, energy, is equal to Planck's constant times c divided by lambda. Same equation, we just replaced the frequency with c over lambda. Now, I said that Einstein said that light can act as a stream of particles, and he was able to explain the photoelectric effect by treating light as a stream of particles. And so the photoelectric effect is when light is shined on a metal surface, it can knock electrons off of it. But it can only do it if the frequency is right. Low frequency doesn't do anything. Higher frequency, once you've reached a minimum threshold frequency, the electrons start coming off. And if you go above that frequency, the electrons come off with more and more speed, or more and more energy. And so what Einstein said is, well, if you think about light instead of a wave coming in, which should just vibrate the electrons, but as a particle that comes in and hits that electron, it can knock it off of the surface. But when light comes in with low frequency, it doesn't have enough energy for that to happen. When it comes in with higher frequency, it does have enough energy to knock an electron out. And once we get above that frequency, we just knock the electrons out with more and more speed, or more and more energy. Shining the light brighter means we're hitting more photons on there. We've increased the number of photons that are coming per second, not the energy of a photon, just the amount of photons. And so the photoelectric effect is explained by thinking of light as a stream of particles. And each photon is a packet of energy, and since it still has a frequency, you can still calculate its energy by E equals h nu. There's a nu that's curvy, but now we're talking about a single photon rather than a continuous wave. This was something that caused, Einstein to get a Nobel Prize, because it was a completely different way of looking at light, where we were saying light is actually not just a wave, it's also a stream of particles. And so we say light has wave-particle duality. It acts like both a wave and a particle, and that happens. We can pick how we want to analyze it based on the situation we're in. Now, another thing that was messing with scientists around this time was spectra. When we look through a prism at the sun, or light produced by an incandescent bulb, we get all the colors in what's called a continuous spectrum. So from red to violet, we don't miss anything. But when you take an individual element and you heat it up until it glows, you don't get that continuous spectrum. You get individual lines, which means we're only getting certain energies out of the atom. And classical mechanics, physics, can't explain why that should happen. As electrons fall closer and closer to the nucleus, they should emit energy, and that energy would change the frequency of the light that came out, and we should get all of the colors, but we don't. We only get certain colors. That means that electrons can only exist in certain places, and they can move between those places, emitting only certain colors. This was Niels Bohr's idea, and he was able to explain this line spectrum by applying quantization to the atom. It also helped sort of explain the photoelectric effect. Bohr said that the electrons are orbiting the nucleus because protons and electrons are attracted to each other. An electron has to have work done to it, or energy put into it, to move it further from the nucleus. When it falls into a more stable state, so it should emit energy, but it can't emit every energy, it can't emit every frequency, or we would get continuous spectra from every element. Instead, what Bohr said was, well, if you think about this wave-particle duality of light, we can apply it to electrons, and we can say electrons can act like waves as well. And so if you've ever plucked a guitar string, you know it only produces one note because it can only vibrate at a certain frequency. It can produce an overtone or harmonic at other frequencies that can fit on that string. Bohr said, well, let's imagine that these electrons are vibrating around the atom in certain waveforms. They can only do that at certain distances where the string or the wave is the right length or the right frequency, since wavelength and frequency are directly related. And so that gets us these line spectra, because the electrons can exist at this level where they can vibrate or at this level where they can vibrate, but they can't vibrate at a half wave or a quarter wave or a fraction of a wave in between. So this is quantized into these discrete places. And so the photoelectric effect only works with a minimum threshold energy because that had enough energy to move the electron off of that energy level. And we get line spectra because the electrons can only move between energy levels. They can't fall. They can exist here, emit enough energy to exist here, or exist here and gain enough energy to exist here, but they can't exist in between.